This video is about solutions, and we're going to mainly focus on aqueous solutions, solutions that are made in water. So we're going to start out with a little bit of a discussion about water and what makes it unique, and then get into the details of quantitatively and qualitatively describing solutions. Let's talk about water. One of the things about water is that its intermolecular forces make it very unique among substances that are similar to it. For example, its boiling point is extremely high for a molecule of that size. So here's water on the left-hand side. You can see the shape of it, and the size of it is very similar to ammonia, which is NH3. That's on the right-hand side. They're not very different in size. The boiling point of water, as we all know, is 100 degrees C, but the boiling point of ammonia is much lower than that. And the reason is because water can do hydrogen bonding, each molecule, to 4 other water molecules. And ammonia doesn't have that ability. It can do hydrogen bonding, there's only one site, so it can be attached to 2 other ammonia molecules. And that makes the overall intermolecular forces in ammonia much lower, and so it boils at 33 degrees below zero. So ammonia is a gas at room temperature. Another thing that's unique about water, due to its intermolecular forces, is that the heat of vaporization is very high. Heat of vaporization is the amount of energy it takes to vaporize a certain quantity of a substance, usually a mole. For water, the heat of vaporization is 40.79 kilojoules. That's what's required to vaporize 1 mole of water. For H2S, in contrast, the heat of vaporization is only 18.66 kilojoules per mole, and so that substance is a gas, typically, at room temperature, because it just doesn't take as much energy to turn it into a vapor or a gas. So as a result, water mainly exists as a liquid or a solid on Earth, not so much of it as a gas. There's certainly plenty of water vapor around, but its main existence is in the solid or liquid form. Also, water's specific heat capacity is very high. The specific heat capacity is the amount of energy that it takes to increase a certain amount of it by a certain temperature. Usually that's a gram by a degree C. Here, for example, it takes 4.18 joules of energy to make 1 gram of water go up by 1 degree C. Most other substances are much lower than that. They're less than 1. So water is about 40 times higher than a lot of other substances that exist. And the consequence of that for life on Earth is that water keeps Earth's temperature regulated. It takes a lot of energy to make its temperature go up and down, and because the surface of the Earth is covered with a lot of water, that keeps our planet from going down to near absolute zero at night and then going to hundreds or thousands of degrees during the day. Water is also less dense as a solid than a liquid. And this is very unique among substances. Almost everything gets more dense as it freezes, but water doesn't. So in liquid water, there's no form or structure to the particles. They can all kind of move around freely around each other. But when water takes a solid form, it arranges into this space-filling structure that has gaps in between it. And that's because of the hydrogen bonding and the way that it sets up this sort of hexagonal structure. So because solid water is less dense than liquid water, water, as it freezes, floats up to the top of the pond or river or lake or whatever it is, and freezes from the top down. And almost every other substance freezes from the bottom up. This has huge consequences for the possibility of life on our planet, because if water froze from the bottom up, like most other substances, then all the frogs and turtles and fish and everything that lives in those aquatic environments couldn't survive through the winter. Water's intermolecular forces also make it able to dissolve polar substances and ionic substances very well. And since many nutrients and biological molecules are either ionic substances or polar substances, they can easily dissolve in water, and then they can be transported in solutions of water, which is a lot of what we eat and drink, and also our blood and other body fluids. So let's get into some terminology so we can talk meaningfully about solutions. One piece of solution terminology, one vocabulary word, if you will, is solvent. Solvent is the principal component of the solution. This is what most of the solution is made up of. Another way of thinking about this is the background into which stuff gets dissolved. In lots of solutions that we're talking about, this is water. The solute is any substance that got dissolved in the solvent. So this is going to be not the primary component. So if you have salt water, for example, salt is the solute. Sugar water, sugar is the solute, where the solvent would be the water in those examples. Concentration is a measure of the ratio of either solute to solvent. So for example, grams of sugar per kilogram of water maybe, or solute to solution. And that's the one we're going to use a lot more often. So for example, grams of sugar per liter of solution might be a way of expressing that ratio. In everyday terminology, the concentration is basically how strong is the solution. Here are some qualitative descriptions of concentration. One is dilute. In a dilute solution, the concentration is relatively low, which means not as much solute per unit of solution or per unit of solvent. Concentrated is the opposite. When we say something is concentrated, that means relatively high compared with dilute solutions. Now, these are both qualitative descriptions that require some kind of a implied reference point, so you can say what's concentrated and what's dilute. So these are not super useful in terms of quantitatively describing a solution. A saturated solution is a solution that has the highest possible concentration of solute that you can have under current conditions. That means you can't dissolve anymore. So if you were to add sugar to water, stir it up till it dissolves, add more sugar, stir it up till it dissolves, keep doing that until you can't dissolve anymore, that is a saturated solution. Here's another vocabulary word, solubility. The solubility is the concentration of that solution when it is saturated. Now let's look at some quantitative descriptions of concentration. The one that we're going to use most commonly is molarity. Molarity is abbreviated with a capital M, and it's the ratio of the number of moles of solute per liter of solution. So here's a question that involves molarity. What volume of a 0.250 molar, that's how we would read that, solution of KCl is needed to provide 0.0250 moles of KCl? Since this is a ratio, you can use this as a conversion factor in dimensional analysis. That's probably how I'm going to approach this. 0.0250 moles of KCl, and I want to know a volume, so I want to know how is the liters compared with the moles, and that's molarity. So 1 liter, if this solution contains 0.250 moles of KCl. Moles of KCl are going to drop out, and this is going to tell me how many liters are needed, and when I do the math, it's 0.100 liters. If I want to make a solution from a solid or liquid solute, so let's say salt water, or if I'm dissolving some syrup in water or something like that, here are the steps. The first thing I have to do is find the mass of solute that I'm going to have to dissolve. So let's do an example problem here as we're going. Let's say we want to make 500 milliliters of a 0.1 molar sodium chloride solution. Okay, I'm going to start out by noting how much I want, and then I'm going to use the ratio that is given by molarity here, 0.10 moles of NaCl in every 1,000 milliliters, because it's moles per liter, and I want milliliters to cancel, so I'm just going to make that little conversion right in my problem setup. And then the molar mass of NaCl is 58.35 grams per mole. So moles are going to cancel, milliliters are going to cancel, and this is going to give me grams of NaCl, which is what I want. And when I calculate this out, it's 2.92 grams of NaCl. So that's the first thing that you need to do. Next, you add that quantity to some water in a special flask called a volumetric flask, which you may have used before in lab already. So I'm going to weigh that out, and then I'm going to pour it inside of this flask. And the flask isn't going to be full of water, but it's going to have some water in there. Once I've done that, I'm going to swirl it around until I can't see any solid anymore to dissolve that solute. Okay, so now I have the mass of solid that I needed in there, and it's now dissolved, but the volume isn't right. So the next thing to do is to fill this volumetric flask up to the mark that's on the volumetric flask. So this very precisely will give me volume, in my case 500 milliliters. So I want to make sure that I chose a 500 milliliter flask for this job. And notice how the bottom of the meniscus is what touches the mark. That's how those things are calibrated. So when the bottom of the meniscus is on the mark, that's very precisely 500 milliliters. And then once you've done that, put a stopper, or sometimes I just put my thumb over the top and then invert it several times. And the point of this is to get that more dense solution down in the bottom mixed in with the pure water that you added on the top, and just make a consistent concentration throughout the entire flask. Here's a procedural note about volumetric flasks. They are not designed to contain solutions over a long period of time. They're not storage devices. So after you make this solution, you'd want to put it into a different container and then immediately rinse out that flask with distilled water, and then dry it off and store it, because it's really only for measuring volumes. It's not for storing solutions. Another way you might be asked to make a solution is by diluting a more concentrated solution. So say you have really strong acid, let's say, and you want a weaker solution. You can take a little bit of that strong solution, add water to it in just the right amount, and then make a weaker solution, make a less concentrated solution. Here's a little bit of a shortcut. Since the molarity times the volume is the number of moles, and since the number of moles of solute can only come from the concentrated solution, the number of moles in the concentrated solution and the number of moles in the dilute solution have to be the same. So we can set those equal to each other, and we get this little thing here called the dilution solution. The molarity of the concentrated times the volume of the concentrated is equal to the molarity of the dilute solution times the volume of the dilute solution. So for example, say we want to make 250 milliliters of 3 molar HCl from some 12 molar HCl. So this is like a real life situation. When we buy HCl, it comes in 12 molar, but that's usually way, way too strong for most of the things that we need to do in lab. So let's set this up. The molarity of our dilute is 3.0 molar. And the volume of dilute that I want to end up with is 250 milliliters. The molarity of my concentrated is 12 molar, and the volume of the concentrated is my unknown. That's the thing that I want to find. So if I divide both sides by 12, that's 3 over 12, that's 1/4. So this ends up being 62.5 milliliters of our concentrated solution. That's what I need. So the next thing I'm going to do is I'm going to measure out that 62.5 milliliters of my concentrated solution using some device. Sometimes it's a pipette, sometimes it's a graduated cylinder like we see here. And then I'm going to add that to a volumetric flask that has some water in it. And I chose a 250 milliliter flask because that's how much volume I want to end up with. Mix it around good, just like if it was a solid solute. Then I'm going to fill it up to the mark and make sure that the meniscus is touching the mark for the proper measurement of volume. And then I'm going to stopper it and invert it several times to make sure that it gets mixed thoroughly. Now let's talk about why solutions form and the energy changes that are associated with solutions forming. One of the reasons that solutions form is because random arrangements of particles are more likely. So imagine that you have a box with a divider in the middle, and on one side of the box you have these green particles, and imagine that they're free to move anywhere that they want to move. And on the right hand side you have some gold particles, same thing, they can go anywhere they want to go. If you remove the divider and wait a bunch of time, which of these two situations is more likely? That the green particles, after randomly moving around for a while, and the gold particles, after randomly moving around for a while, have gone back to their original positions? Not very likely. It's much more likely that you're going to have green and gold particles kind of randomly distributed throughout this entire box. So solutions are a more random distribution of particles, and that means they are more likely to form. But that's not the only thing that is involved in this. There's also an energy consideration. If we take particles that are attracted towards each other, so like two things that can do hydrogen bonding or two things that can do London dispersion forces, and you allow them to move towards each other, closer together, that reduces how much energy is stored in the fact that they've been held apart from one another. And lower energy situations tend to be more stable. And so that's another factor that helps solutions form. So the energy imbalance between breaking up the IMFs between the solute and solvent and then forming the IMFs in the solution can make the formation of solutions either more or less likely. So the randomness thing, that's going to tend to favor all solution formation. But this energy thing, sometimes it doesn't. Sometimes the energy situation keeps solutions from forming. Let's look at some details of that. Say we have a polar solvent and a nonpolar solute. Two things have to happen. The first thing that would have to happen is you have to break up the relatively strong IMFs in the solvent to expand it. Why are they stronger? Because they're dipole-dipole interactions and maybe hydrogen bonding. And that's going to take quite a bit of energy to break them up. So you have to move the solvent particles far enough apart from each other that there's room to fit the solute particles in between. But you also have to break up the London dispersion forces, or the dispersion forces, to expand the solute enough to make room for solvent particles. When you do that, that's not going to require as much energy because dispersion forces are a little bit weaker. Now we're going to form some intermolecular forces in our solution, but they're going to be relatively weak because the attractions between the polar and nonpolar substances are just dispersion forces. So it's not going to be a very big energy drop. So this is a relatively large energy disadvantage to the solution forming. And what that means is polar and nonpolar solutions are unlikely to form because it takes more energy than you get back. Even though the randomness thing is in favor of it, the energy is not. And so we don't usually see solutions of polar and nonpolar substances. Here's another example. Polar solvent, polar solute. You have to break up relatively strong IMFs to expand the solvent. You have to do the same thing for the solute because it is also held together by dipole-dipole or maybe even hydrogen bonding. But when you form the solution, the intermolecular forces between solute particles and solvent particles are strong IMFs. And so that's a big energy release when you get those substances to go back together close to each other. So there is very little or sometimes no energy disadvantage or sometimes even an energy advantage to the solution forming. And so polar solutions, where a polar solute and a polar solvent are being mixed, those are very likely to form. Let's look at nonpolar solvent, nonpolar solute. To break up the solvent doesn't require very much energy because it's just dispersion forces because it's nonpolar. To break up the solute, same story. It doesn't require very much energy because, again, dispersion forces are pretty weak and they're the only thing that holds together those solute particles to each other. When we form the solution, there's not that much of an energy release because, again, it's just dispersion forces attracting the golds to the greens in this picture. But we didn't have to add that much energy in the first place, and so the energy disadvantage, there's very little of it, or maybe sometimes none, or maybe sometimes even negative. And so nonpolar and nonpolar solutions are likely to form. A nonpolar solvent in a nonpolar solute will mix pretty readily. So when we put those things together, there's this sort of a shortcut that people like to use where they say like dissolves like. It's a little bit of an oversimplification because you can fool yourself sometimes, but usually things that have a similar structure will dissolve in each other, whether they're polar or nonpolar. So polar dissolves polar, nonpolar dissolves nonpolar, but polar doesn't dissolve nonpolar very well. Here's a factor in solubility. For liquid solvents with a solid or a liquid solute, in general, as the temperature gets higher, the solubility usually increases. Now, that's not always the case. We can see a counterexample here with this cerium compound. But almost everything else, as the temperature goes up, the solubility also goes up. Let's think about why that is. We have to break some intermolecular forces to expand the solvent a little bit. We also have to break some intermolecular forces, or if it's an ionic compound, we have to break up the lattice energy, which is a much larger number, to expand the solute. Then, as we form the solution, we form some intermolecular forces. And these forces are called ion dipole attractions, if it's ions attracting a polar substance, or sometimes they're just dispersion forces or dipole-dipole interactions or hydrogen bonding. Because less energy is released than you had to put in, typically these are endothermic. In other words, there's a net energy in to form these solutions. So that means at higher temperatures where you've added extra energy, that means the solubility is going to go up because you just have more energy to make this transition happen. Let's look at what happens with a liquid solvent and a gaseous solute. So let's say dissolving oxygen or carbon dioxide in water. What are the steps? First, you have to break up the IMFs to expand the solvent to make room for the particles of the gas. But the particles of the gas are already separated from one another. So we don't have to add any extra energy for that. But then you form these IMFs to create the solution, and usually there's a net decrease in the amount of energy that the system stores. So this is a process that releases energy, and so that means at lower temps, more energy is removed, and that means more solution will form, and so the solubility actually goes up when the temperature goes down. So here are several gases dissolving in water, and their solubilities as temperature increases, you can see that they drop off, so you can dissolve less gas in warm solvent than you can in cold solvent. Related to gas solubility is this law called Henry's law. Henry's law says that the concentration of a gas at equilibrium is proportional to its partial pressure above the solution. What this really means is that the concentration of the gas is equal to some constant number, it's called the Henry's law constant, times whatever the pressure of that particular gas is above the solution. So in the case of a carbonated beverage like champagne here, the carbon dioxide pressure in the space up above the liquid is very high. That's why the cork pops off, and that allows a large amount of carbon dioxide to be dissolved in the champagne. Once you pop the cork off, much less can stay dissolved in there, and so that's why you get all these bubbles foaming out of the champagne or whatever carbonated beverage it is when you release the pressure. Because as the pressure drops, that means the allowable concentration, the solubility, will also go down. And so it comes out of the solution and you see it as a gas, which is bubbles. One last topic is electrolytes. Solutes that when you dissolve them form electrically conductive solutions are called electrolytes. Electrolytes are a word that's used a lot and not a lot of people know what it means. You will know what it means after this. Here are things that are electrolytes. One is ionic compound. This is mainly what we're talking about when we talk about electrolytes, is ionic compounds. The reason that these are electrolytes is because the ions, when they're released from the lattice structure during dissolving, they become mobile. And moving charged particles is what electrical conduction is. Here's an animation of this. Water molecules are polar, as we have learned. They have a negative and a positive side. Ionic compounds are also polar in a way. They're extremely polar. In fact, they're full charges of ions. So imagine this as a sodium chloride crystal. Water molecules come in there. The positive hydrogen ends are globbing onto the chloride ions and pulling them away, but the negative oxygen ends will stick onto the positive sodiums and pull them away. And then out in solution, they have these what are called ion dipole interactions because it's an interaction of an ion with a polar molecule, a dipole. The waters make a little shield around each of the ions, and that keeps them from going back together until it's too crowded for the water molecules to continue to do that, and at that point you've reached saturation. Another type of electrolyte is a strong acid. Strong acids don't actually dissolve in water as much as they react with water. So if we have an acid, which we're going to kind of model with HA, because it's a hydrogen attached with some anion, the A stands for some generic anion, 6 of them in particular, it will react with water, and water will gain the proton, the H, from this acid. It'll attach to water, so now water is H3O, but because it leaves its electrons behind in that bond, then that means that this has a positive 1 charge because it got a proton, but it didn't get any more electrons. And then this anion kept the electron that it was sharing with hydrogen, and so it now has a negative charge. So now you have charged particles in solution, and they can conduct electrical current. Here's an example of that. Hydrochloric acid is a famous acid. So the hydrogen is going to break away and attach to that water, and that gives you that H3O plus ion. It's called hydronium ion, and it also leaves you with a chloride ion. So those are charged particles. They can conduct electrical current. So you might be wondering, why does this happen? And the reason is that that proton is more attracted to electrons that are shared by the smaller oxygen atom than the larger Cl atom. So this oxygen is smaller. That means those electrons are closer to the nucleus of that oxygen. That's a shorter bond, and that makes it a stronger bond. And so this hydrogen is more attracted to that oxygen than it is to this chlorine, and so therefore it's going to make the switch. There are 6 strong acids, 6 acids that do this completely to produce electrolytes, and you should know what they are. The first one is HCl that we just saw in the example, hydrochloric acid. There's HBr, and there's HI. All 3 of those come from the column 7 elements in the periodic table, covalently bonded to hydrogens. Then there's nitric acid, HNO3, and sulfuric acid, which is H2SO4. These 5 are the most common ones. Then there's one more that's a little more obscure. You don't see it very often, but it's perchloric acid, which is HClO4. Those 6 will always do that acid thing and become electrolytes in water. They're called strong acids. There are lots and lots more acids in the world, but these are the ones that completely turn into an electrolyte once you dissolve them in water.